Hello and welcome to Inside Track at EmTech Digital. Your look at the coolest, most cutting-edge tech coming out of MIT. My name's Neil Firth and I'm the news editor at MIT Technology Review based here in London. So today we're going to be speaking to Jesse Thaler, the inaugural director of the NSF AI Institute for Artificial Intelligence and Fundamental Interactions here at MIT. At IAIFI, as it's known, scientists are combining the latest in machine learning with our fundamental understanding of physics and seeing what the collision between the two spits out. Speaking of collisions, in his own research, Jesse fuses quantum field theory and machine learning to study the jets that are produced in the high-speed collisions at particle colliders like the LHC. Together with his colleagues, he's using AI to learn about everything from the smallest building blocks of nature through to the biggest structures in the universe, and teaching machines to think like physicists, as he'll tell us about shortly. Jesse, welcome to EmTech Digital.
Great. Thank you very much, Neil. And it's a pleasure to be here to tell you about artificial intelligence meeting fundamental physics. As Neil said, I am the director of the NSF AI Institute for Artificial Intelligence and Fundamental Interactions. And this is a joint venture between MIT, Harvard, Northeastern, and Tufts, where we're trying to fuse physics knowledge with AI research innovation in one institute. And you can see this by our logo here, which, depending on how you read it, you can either see it as a capital A with an I on top of it for artificial intelligence, or an F with an I next to it for fundamental interactions. And hopefully in this presentation, you'll get a sense of how both of these are flip sides of the same coin. Now, one of the things that we're trying to do in our institute, IAIFI, is to try to figure out if it's possible to teach a machine to think like a physicist. So oftentimes when we think about AI, we think about trying to teach a machine to have the creativity that we see in children. But it's challenging to reason with a toddler. And we'd rather have, as physicists, AI where we can understand what the machine has learned and have the type of rigorous analysis that we expect for physics analyses. And so that's one of the goals of this institute, to figure out how is it possible to encode physics principles into a machine. More provocatively, there was an article from the New York Times last year that posed the question, could a computer ever devise a theory of everything? This is one of the goals that we have in theoretical physics. And this sounds a little bit outlandish. You know, how could you possibly have a machine that could have the type of creative thinking that the founders of the standard model of particle physics had? But what we're going to try to explain in this talk is that it is possible to encode physical principles into machine learning architectures. And we'll see where that gets us in this presentation today. So to try to highlight this, let me give you an example that's not coming from my field. This is going to be an example coming from image processing, where we can see what it means to encode physical principles into a machine learning architecture. So I think we're all familiar with the rise of deep learning, where computers are able to accomplish amazing tasks. Here's an example of what's called an image infill task, where we have an image on the left-hand side that has been corrupted because there's regions of that image that have been masked. And what we have on the right-hand side is the reconstructed image, which looks like a pretty passable library where indeed the masked regions have been filled in correctly. And the standard lore that we have in deep learning is that we have incredibly large data sets. We have many, many images, in particular, many images of libraries, plus increased computational power that we can use to try to figure out what is the best image that corresponds to the maxed starting point. That is, what is the image that is most close to the prior that we think images should look like. But what I like about this example is that this is an example where it fuses deep learning with what I might call, as a theoretical physicist, deep thinking, where actually, in this particular case, the machine has never seen any other images whatsoever. Rather, the authors of this work have understood the structure of this problem and realized that if you're trying to figure out what's hiding behind these masked regions, what you want to do is you want to use the translational symmetries of bookshelves and try to capture pieces in one part of the bookshelf and translate it over to fill in the gaps. This translational symmetry is something that physicists are very familiar with, and that's something that we want to capture in the type of machine learning architecture we want to use for physics applications. So to give you a little bit more context from my own research, let me tell you a bit more about the standard model of particle physics. This is one of the pillars of fundamental physics, what describes nature at the shortest distance scales. This pie chart here shows you the particles in the standard model, the quarks shown in orange, the leptons shown in green, the force carriers shown in blue, and the Higgs boson at the center of the standard model shown in purple. But one of the challenges that we have in trying to understand collision debris at colliders is that you don't actually see these ingredients directly. Rather, only a small subset of these particles are actually seen in colliders. And even then, their manifestation can be complicated. So particles like photons, electrons, and muons, the ones that experience the electromagnetic interaction, those ones we can see directly. But quarks and gluons, which are elements of the strong force, while they play an important role in particle collisions, we don't see them directly. The strong force is strong. It binds quarks and gluons together to form composite states that are known as hadrons. An example of a hadron is the proton, and the Large Hadron Collider is a collider that slams together protons, slams together those composite states. And there's other ingredients here on the left-hand side that aren't even represented on the right-hand side because they're unstable. Once they're made, they decay incredibly quickly. So for example, the Higgs boson is a particle that only exists for a fraction of a moment before it disintegrates into other states. And so trying to figure out this amazing structure of the standard model of particle physics and its possible extensions beyond it when we don't have access to the full information, this is a challenging information for which machine learning has a chance to help. So here's what an actual collision looks like at the LHC. So this is a collider event. And these collisions happen every 25 nanoseconds. And so if you're trying to make decisions about what's going on, you actually need fast AI to make robust decisions. And you see this beautiful spray of particles coming from the collision point. And you also see these collimation effects, these collimated sprays. And these collimated sprays are what are known as jets. Jets are the manifestation of quarks and gluons when they're made at high energies. And even though I don't see quarks and gluons directly, I can infer their presence by the presence of these jets. Now, from a data science perspective, this collision that you see right here can be thought of more generally as just a collection of points in momentum space. That is, we have the momenta of each particle. They have momentum in the x direction, the y direction, and the z direction. And we can use those momenta to reconstruct what's going on. But there's other contexts where we have things living in a space, not living in momentum space, but living in position space. And that's what's known in the machine learning world as a point cloud, a collection of points in position space. For example, here in this image from a LiDAR detector from a self-driving car, where we have points in X, Y, and Z. And there's many similarities between trying to parse an image from a self-driving car versus trying to parse the collision debris at the LHC. So for example, one thing you might want to do if you're given a collection of LiDAR points is that you'd like to identify objects in your scene. And that object finding is similar to what we do in the particle physics context where we do this jet finding procedure. Similarly, I told you that jets could are the manifestations of quarks and gluons, but we'd like to know whether a particular jet comes from a quark or it comes from a gluon. That's similar to what we have in the self-driving car context, where once we've identified an object in the scene, we'd like to know, is it a bicycle? Is it a car? Is it a pedestrian? And that's known as a classification task. So there's many similarities with the types of techniques that we'd like to do, both in the self-driving car context or more generally with point cloud learning, and what we'd like to do in the particle physics context. But what we can do is we can take advantage of our knowledge of the intrinsic underlying physical structure of the problem that we're trying to solve. And that gives us a new way of approaching the problem and allows us to do better inference than we would if we didn't have that physical principle at play. So to explain this, I need to tell you a little bit more about the dynamics of jet formation. So as I already mentioned, protons are these composite states that when you slam them together, you liberate the quarks and gluons that compose the proton. Those quarks and gluons are produced with high energy. They undergo a process called showering, where more and more quarks and gluons are produced to form out this jet. These quarks and gluons eventually confine by strong force and make these composite hadrons. And those composite hadrons ultimately hit your detector, and you have to infer what was going on at short distances in the initial collision by the particles that you detect in the final state. So this is a very complicated generative process. And you might want to think about what physical principle can I use to try to understand these collision debris more robustly. And the tool that we have from theoretical physics is an understanding of what information is most robust. And it turns out that predicting this whole pattern is quite complicated, but something that we do have more theoretical control over is studying the flow of energy from the collision point off to infinity. This energy flow information is robust to the hadronization step and robust to the detection step. For those of you who might have a physics background, the energy flow operator here is built out of the stress energy tensor T mu nu, where the zero component is energy, the I component is its flow. This is something that we've known about for a long time in theoretical physics, and something that we can use to build an advanced AI architecture to process collision debris. So as Neil was alluding to, what we have is we have a collision. We have a collision between principles of fundamental physics and the power of artificial intelligence. From fundamental physics, we have this understanding about the robustness of energy flow. And this is something that comes ultimately from the structure of quantum field theory. It is one of the pillars of the ways that we make theoretical predictions in fundamental physics. Coming in from the artificial intelligence side, we have advances in point cloud learning. And the particular technique that we're using here is a technique called deep sets, which was developed at Carnegie Mellon. And we can fuse together this fundamental physics principle with artificial intelligence and see what comes out. It turns out that you need a little bit more ingredients into this collision. So you need some fantastic graduate students. So my graduate students, Patrick Comiskey and Eric Metodiev, contributed their creativity and computing skills to this work. You also need funding to run the types of simulations as well as to do the AI training for these efforts. And then finally, from this collision out pops a neural network architecture as well as a corresponding web page that we call energy flow networks. And these energy flow networks are the synthesis from fundamental physics and AI, and represents an example of the types of things that we're trying to accomplish with our Artificial Intelligence Institute, IAIFI. So let me try to show you now what the machine has learned from this fusion. And this next image is one that even experts have a difficult time interpreting, but I think it's fun to try to explain what's going on here and try to explain what the psychedelic image is representing. So kind of let your eyes look at this for a little while. And this is a representation of what the machine has learned in the process of analyzing jet data. And what you should be thinking about is the jet is actually going into the page. The center of the jet is going into the central region of this image. And then these rings that you see are a representation of where the AI is paying attention to information. So if we had a standard camera, and you ask, how does a camera pay attention to information? A camera pays attention to information pixel by pixel. So if we were going to draw the same representation for a camera, an ordinary camera, what you would see is a regular grid of boxes. Here, we don't see a regular grid. Rather, we see these circles, which are more dense in the center of the image and sparser towards the periphery of the image. And when Patrick and Eric showed me this image for the first time, this representation of what the machine learned, I nearly fell out of my chair, because what the machine has learned is it's learned the fractal structure of the strong force. That is, the strong force doesn't populate radiation in a way that's uniform in pixels like a camera would take. Rather, the radiation follows a very characteristic pattern where there's more information. It's more information rich towards the center of the jet versus the periphery. And that's indeed what the machine has learned how to do. We put this artificial intelligence technique together with a principle of physics, and then the machine learned for itself another principle of physics, namely the structure of the strong force, the fractal structure of the strong force. So let me say a little bit more about what you're seeing here. So what we've trained the machine to do is to just solve this simplest of jet problems, what you might call the hello world of jet physics. Just the simple classification task of whether it's seen a jet that's a quark versus a jet that's a gluon. The particular neural network architecture that we're using is these energy flow networks that my students and I developed. And the structure of these energy flow networks encodes some of the basic principles of fundamental physics. In particular, you can see this energy weighting term here. And this energy weighting term is what you need in order to have this energy flow as playing a central role in the way that the AI is making a decision. And what's really nice about this network architecture is that ultimately, the network architecture is going to spit out an answer, this S function that's trying to tell me whether I've seen a quark or a gluon. But this S function is built out of these V functions, V standing for verification. And what's being plotted on the left-hand side here is those verification functions. It's saying, hey, machine, where have you paid attention to information within the jet? What part of the energy flow are you focused most on? And what it's learned is that it should focus on the energy flow more in the center less in the periphery. And the precise pattern about how much more information is captured by the center versus the periphery turns out to correspond precisely to what we already know from the structure of quantum field theory. So it's very satisfying that the machine has effectively taken a course in quantum field theory by just analyzing collision debris coming from jets from the LHC. So what we've accomplished here is we taught a machine to think like a physicist. We taught the machine to not only solve a task, but also provide information to verify that the task was successfully completed. When we did that, it learned the fractal structure of the strong force. So we gave it some physics principles, but it learned additional physics principles on top of that. And then you can imagine incorporating this fractal structure back into the machine learning and actually potentially exposing new, deeper principles at play. And this synergy between AI and fundamental physics is indeed what we're trying to do with our AI Institute. And there are many synergies that we're exploring. And they have this commonality that when you have really rich data sets and you have deep fundamental principles, then you have a chance to advance both on the AI side and on the physics side. And so here are just a couple of the things that we're working on in our institute. One example comes from gravitational waves. And there you have the principles of general relativity, basically Einstein's theory of gravity. And that tells you how, when you have two black holes that are inspiraling, how the gravitational waves are produced. And this is a case where we have rich data sets from the LIGO gravitational wave detector, rich physical principles coming from the structure of gravity, and we can synthesize those together, we hope, to do a better job in understanding the gravitational waves produced by these violent events in the universe. In the case of nuclear physics, you're going to be hearing later this week from my colleague Fiala Shanahan, who uses ab initio calculations of the strong force to understand the structure of nuclei. And this is now a situation where we have incredible synthetic data sets that can be created on supercomputers. And you can analyze those synthetic data sets in exciting new ways to expose the structure of nuclei. We have researchers in IAIFI working on astrophysics, on the mystery of dark matter. I told you about understanding particle collisions. We also have people who are working in mathematical physics, where it turns out that there's complicated mathematical problems that you'd like to solve, where we have rich data sets about those problems already being solved by humans. For example, here is showing a problem of trying to figure out whether a particular string is knotted or not. That turns out to be related to questions in string theory. And this not solving problem is one for which actually techniques from natural language processing turn out to be relevant for understanding whether a configuration is knotted or not. And so hopefully this presentation is giving you some sense about the types of principles and strategies for physics that one might want to explore and their relevance for physics. But what I want you to think about is what principles and strategies from physics could be incorporated into your data science and AI applications. In this presentation, I focused on things like symmetries. That's something that comes from physics. I focused on things like verifiability, checking that your answer is correct. Another thing that physicists care a lot about is understanding uncertainties and how do you quantify that. And that's something where physics understanding and physics best practices we expect will have broad applications beyond our particular application domain. So with that, looking forward to bringing Neil back into the conversation to tell you more about this intersection of AI and fundamental physics. Thanks very much.
Thank you, Jesse. That was brilliant. Really, really interesting stuff. I was really particularly fascinated in the way you talked about the other sort of aspects of research that your institute are doing. What are some really big questions in physics that you feel like this approach could help with in the future?
Right. So I mentioned already the example of gravitational waves and about ab initio calculations of nuclear matter. But one of the big questions, in some sense, it's going to be the defining question for my generation of fundamental physicists, is what is the nature of dark matter? Dark matter is a substance. It's 5 times more abundant than ordinary matter. We've detected it gravitationally, but we don't know what it is, whether it's a fundamental particle or something else. And what we're hoping is that AI techniques can help us both understand what dark matter is doing in the early universe, as well as help analyzing data from observations and experiments to try to unearth what dark matter might be, whether it be a particle or something else. And so that's a key application that we hope that this fusion of fundamental physics principles and AI techniques will help uncover.
Great. And the neural networks, machine learning you're using, it seems to me that you're Is it unsupervised? It seems to me that you're not telling it what to look for. It's just finding its own patterns and its own points of interest. Is that right?
Well, so the example that I gave with quarks and gluons, the particular plot that I showed you was actually a supervised learning example where we gave it data that was already labeled by quarks and gluons. But you asked a fantastic question, which is, wait, I don't know what quarks and gluons are ahead of time. That's what I'm trying to understand. So wouldn't it be better if I did an unsupervised learning strategy? And in fact, that was the very first paper that I wrote when I got into this area, where I was extremely skeptical about the role of AI because it seemed like you had to tell the AI what the answer was, and then the AI would just spit back what you told it. And the first paper that I wrote was an example of how you could actually take contaminated data sets or mixtures of data sets that had both quarks and gluons and potentially something else in there, and use unsupervised techniques to disentangle all the various components. And that's what made me a convert to this area. It just happened to be that the psychedelic image that I showed happened to be from supervised learning, but you can do similar techniques even with unsupervised techniques.
Right. And is the idea that the unsupervised part will then be able to spot things that maybe you hadn't thought to look for before, or see patterns that you didn't know were there?
Yeah, and even more so, we've realized that some of these unsupervised techniques can actually give us insights into fundamental physics that are simply not obtainable using ordinary strategies. And in fact, there's an unsupervised learning technique called optimal transport problems, where you're trying to take, in this case, jet configurations and transport one jet configuration and distort it to another jet configuration. And it turns out that optimal transport technique, which is equivalent to if you're a shipping company trying to figure out the optimal way to deliver your goods from warehouses to consumers, solving that problem turns out to be related to some deep principles in quantum field theory. And that was a surprise that a technique that's coming from the AI community actually shed considerable light on some questions that we had about the fundamental structure of the universe.
Oh, great. I mean, you seem to be suggesting as well that it isn't just about applying machine learning to help with the physics, but there might be some sort of reverse procedure as well. They might be able to also help with AI. Are there any ways in which some of the stuff you're going to get out of the core science physics problems can help advance machine learning itself, or even trickle down into other areas of technology?
Yeah, I think there are interesting parallels between the questions that we ask in physics and the kind of questions that people are asking right now about AI. One of the things that people care a lot about is trustable AI, or AI that you can interpret. And this is something that we care a lot about in the fundamental physics applications. We'd like to make sure that if an AI makes a discovery of some new particle, AI played a key role in the discovery of the Higgs boson, we want to be able to verify that actually what the AI has discovered is real and not some type of artifact. And so if we can figure out how to translate the way that physicists think about uncertainties and translate that to the broader community, I think that will be a great advance in our ability to develop trustable AI technologies.
Fantastic. Well, it's all really fascinating stuff. I'm afraid that's all we've got time for in our chat right now. So we'll stop there and say thank you very much, Jesse Thaler, for joining us. I really enjoyed having you with us.
Great. Thanks so much, Neil. It was a lot of fun.
Okay. And thank you, everybody, for coming to this Inside Track. Thanks to Jesse again for coming to see us, and I hope you enjoy the rest of today's main stage program. Goodbye now.